So this is lecture number 27, Signals and Systems 205 to 16, sections 450. Today's Sunday, 21st of April. Now we're beginning the new chapter. This chapter is about discrete time systems, discrete time signals. Basically, suppose we have a continuous time signal that is represented by a dashed line here on its graph, and suppose we sample this signal every t time units. Okay, so these points are called samples. And we represent so x of s t is just the sampled version of the signal x of t, and it's just the value of the signal x at the time n capital T, where n is an integer. Now we are interested in only these samples, the values of these samples. We're not interested in the time, the particular time. We're just interested in the order of the samples. In other words, we are only interested in the integer value n that represents the order of the samples. So we're gonna write x with the straight bracket n to represent the discrete time signal, where n is an integer that represents the order of this sample. For example, n of 1 comes before n of 2, n of 2 comes before n of 3, and so on. N of 0 comes before n of 1, n of minus 1 comes before n of 0. So n here represents the order of the sample. Now, x of n0 is just the value of x of t at time t equal to nt0. And you have to be careful that x at order n is not equal to x at time n. See, there's a little confusion in the terminology or notation here. Whenever we write down a curly bracket here, it means that this is going to be the value of the time. So x of parentheses n would be the value of x at time n, whereas x at the straight bracket n means the x of the order n. The nth value, the nth sample of x is not equal to the value of x at time n. You have to be careful about this. Okay, and we can also graph discrete time signals where the horizontal axis would be the order of the samples. For example, here n represents the order, and x of n may be graphed like this. So for example, x of 0, so the 0th sample of x is 0 here. The first sample of x is minus 1, and the negative 1 sample of x is 1, and so on. So this is one example of a discrete time signal. Another example would be this. Okay, so this discrete time signal is called h of n, and the value of h at n equal to 0 is 1. The value of h at n equal to 1 is minus 1. The value of h at n equal to 2 is 2. Now, it is very important that discrete time signals do not have values. The values of them are not defined where n is not integer, so you should write that down. Discrete time signals are not defined when n is not an integer. You have to be careful about this. You have to keep this in mind. Okay, they are only defined when n is an integer only. For example, x of 1.5 is not defined. We don't talk about x of 1.5. Okay, the value inside the straight brackets have to be an integer. So from the graph here, we can see that we can actually define discrete time signals using algebraic in an algebraic form. For example, here in this case, you see x of n would have to be equal to n. Actually, it has to be minus n, right? Minus n. So I should erase this, change it to minus n. There's a typo. Minus n. Okay, it has to be minus n here. This is x is equal to minus n, where n is 0, plus minus 1, plus minus 2. And the rest, the value of x for other n's would be 0. So the rest here is 0. On the other hand, the signal h can be defined algebraically like this. When n is 0, h is 1. When n is 1, h is minus 1. And when n is 2, h is 2. The rest is 0. Okay, the rest is 0. So there are two ways, at least now, to define discrete time signals. Or you could define using equation. Okay, or another example is to use algebraic equation, or we can use equation to define a discrete time signal. For example, you may say y of n is equal to 0.3 to the nth, where n is 0, 1, 2, 2. We can also use algebraic equations to define discrete time signals. Okay, for instance, we may say that y of n is equal to 0.2 to the n, where n is 0, 1, 2, 3, and so on, and 0 otherwise. Okay, in which case, if we want to plot a graph of this signal y, the graph would look like an exponential function, but it is a discrete time version. So if you plot only the envelope, the envelope would look like this, but the actual graph would consist of samples at discrete instances, like this. No. For a negative, y is 0. here. So I can write down 1, 0.2, 0.2 to the second, 0.2 to the third, 0.2 to the fourth, and so on. And this is a graph for y here. Or you could say that, say that z of n is equal to n, where n is 0, 1, 2, and so on, and 0 elsewhere, n square. Then if you plot z, it would look like a parabolic function, except that the values are discrete instances. Okay, and so on. And 0, we must not forget about zeros. So this is 1, 0, 1, 2, 3, minus 1, minus 2. So this is 1, this is 4, this is 9, and so on. This is z. All right. So we have at least 3 ways to define discrete time signals. First is to use a graph. Second is to use algebraic equation. And third is to use the direct assignment of values. Okay. Now, one concept about signals is periodicity. We talked about periodicity in continuous time signals. Turns out that we can also talk about periodicity in discrete time signals. And we say that the discrete time signal x is periodic in n if there exists an integer capital N such that x of n is equal to x of n plus capital N for all n. Okay, the capital N is called a period. Well, I should say a period, not the period. A period. Because there could be several values of n here, and the smallest of such n would be called the fundamental period of x of n. Now, to understand periodicity of discrete time signals is very simple. Okay, you just look at the graph of x. For example, if the graph of x looks like this, here, there and there. Oh no, not this one. This one. And so on. Now, this signal is a periodic signal. It's periodic, okay? And the fundamental period of this signal is 3. Okay, this is the fundamental period. Go from going from here. This is 3, obviously. Here. And it repeats itself every 3 samples. Repeats itself. Repeats itself every 3 samples. So its fundamental period is n0 is equal to 3. Okay, let's call this signal x. Y. Let's call it y. Okay. Or x of n could be minus 1 to the n. Now, this one is periodic with period equal to 2. So if I plot the signal x, there, minus 1 to the n. Now the graph will be here. It will oscillate between 0 and between 1 and minus 1. Okay. Here and here. Here and so on. Yeah, this is x of n equal to minus 1 to the n. You see, if n is an even number, then x of n would be 1. But if n is an odd number, then x of n would be negative 1. So swings between minus 1 and 1. One, two, three, 4, 5, minus 1, minus 2, and 0. Okay. Now, energy of a discrete time signal. If you recall, if x is continuous time, for continuous time signals, if x is a continuous time signal, then the energy of x is defined as the integral of x of t squared. The integration is with respect to t. But when the signal is discrete time, is a discrete time signal, then instead of doing integration here, we're gonna do summation here, and the magnitude square is the same, except that the domain, the variable that we are summing, instead of t, it's now going to be n. The magnitude of x of n squared, and it is summed over all n. So this is how the energy of a signal, of a discrete time signal, is defined. Now, because this is an infinite sum, it may or may not converge. But if it converges, in other words, if the energy is not going to infinity, then the value of x is called an energy signal. I'm sorry, the signal x is going to be called as an energy signal. So an energy signal is a signal where the energy is finite. Okay, and a necessary condition for x to be an energy signal is that the value of x should vanish when n goes to infinity. Now, keep it in mind that this is a necessary condition, but not a sufficient condition. Okay? In other words, even though this equation is true, it may not guarantee that x is an energy signal. But if x is an energy signal, then this condition has to be satisfied. Okay? Now, let's look at an example. I'm going to give you two examples. Okay, the first example is I'm going to define x of n as n when n is 0, plus minus 1, plus minus 2, and plus minus 3. And the rest is 0. Now for this one, I'm going to find the energy. Okay, the energy is defined as summation of absolute value, the magnitude of x squared. Now, because the signal x has only 1, 2, 3, 4, 5, 6, 7 samples here, only 7 samples, so we're gonna have the magnitude of x minus 3 squared plus the magnitude of x at minus 2 squared plus blah 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 until magnitude of x at 3 squared. And because the rest is 0, I don't have to write those down. Okay, only 7 of these are not 0, so we can write this down, but the rest is 0, so I don't have to. Now let's plug in the values for these. X of minus 3 is minus 3, right? Squared. X of minus 2 is minus 2 squared. X of minus 1 is minus 1 squared. X of 0 is 0 squared. X of 1 is 1 squared. X of 2 is 2 squared. And x of 3 is 3 squared. So evaluate these numbers. We have 1 plus 4 plus 9 is 14. Now, you see, this and this are identical, so I just multiply 14 by 2, so the value is 28. So the energy of this one, the signal, is 28. Easy. Now another example. Now let's define the signal x as 0.3 to the n, where n goes from 0, 1, 2, and so on, and 0 otherwise. Now let's try to find the energy of this one. So the energy of x, by definition, is summation where n goes from infinity, minus infinity to infinity, the magnitude of x squared. Now let's plug in. The magnitude of x is 0.3, so 0.3 to the n squared, where n now has to go from 0 to infinity. The reason why I have to start at 0 is because the value of x is legitimate only when n starts from 0. So, but because if n is negative, the value of x is 0, so I don't have to write that one down. Now, 0.3 to the n is just 0.3, right? I'm sorry, no. The absolute of 0.3 to the n is just the absolute 0.3 to the n. So I have this to the second. Now I know that I can switch 2 and n. All right, I can swap the value of 2 and n to get 0.3 squared to the n. Now 0.3 squared is 0.09. To the n. Now, if you recall from your high school algebra, this is a geometric sum, and the value is equal to 1 over 1 minus 0.09. Okay, and I'm gonna use my calculator to see that this is equal to 1 over 1 minus 0.09. This is about 1.1. Now, you may wonder how to go from here to there. Now, I use a geometric sum. The geometric sum goes like this. If I add 1 plus r plus r squared plus r cubed plus r to the fourth plus blah 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 plus r to the capital N. Now, the geometric sum states that this has to be equal to 1 minus 1 to the n plus first divided by 1 minus r. On the other hand, if I add 1 plus r second plus r third plus r fourth plus blah blah blah, okay, indefinitely, now the value would have to be equal to 1 over 1 minus r. Now there is a condition for which this is true, and that condition has to be the magnitude of r has to be less than 1. Okay, if the magnitude of r is not less than 1, then this sum will not converge. But if the magnitude of r is less than 1, then this sum converges to 1 over 1 minus r. Okay, and I use this formula on the summation. You see, this one, r is 0.09. Okay, and because 0.09 is less than 1, so I know this sum converges, and that convergence is 1 over 1 minus r. And after plugging in the values using my calculator, I found that this value is equal to 1.1 approximately. Okay, so the energy of this signal is about 1.1. This is the energy of this signal, the approximate energy. Now, energy is not defined, as we know. Energy is not defined for periodic signals. Instead, if we have periodic signals, then we're going to use something called power, and the definition of power is this. Okay, this is the power for periodic signal. Basically, what it says is that you're going to have to compute the energy of over one period. Okay, only one period, only the energy of that signal over one period. This is the energy over one period, and you divide that energy of one period by the number of samples in that period. Okay, and the result would be your power. So I could write it down like energy of X in one period divided by the samples. Now, an example. An example would be if I have, let's say that I think I wrote it down somewhere here. I'm going to use this one to find the power because I don't want to waste time drawing another. So we're going to try to find the power of this signal y. Now you see y here is periodic, so the energy is not defined because the energy of any periodic signal would be infinity, so we're not going to be able uh, uh, to feel the strength of y. So we're going to compute the power instead. Now let's define one period. So this is one period, right? One period here. This is one period. Actually, should be this. Sorry. One period. Yeah. This is one period. So now energy in one period is, oh, I had to write this one down, right? This is 2, this is 1, this is 3, this is 2, this is 1. So the energy of one period is 3 squared plus 2 squared plus 1 squared. That is 14. This is the energy of one period. So power of y, the power of y is the energy in one period is 14 and the period is 3 samples. So the power of this signal y is 4.67. Okay, so power is energy of one period divided by the period. Okay. The average of discrete time signals, the average is very similar to power. In power, you have to find the energy in one period divided by the period, right? But for average, you just add the values of the samples in one period and you divide that value, the summation, by the period. So this is A, not P, sorry. Average is A. So the average of the signal X is this is summation of X in one period. It's not energy anymore, it's just the values of X added together over period. For example, here in this case, I'm gonna copy this down over here. Okay, let's look at the same example. So the sum over one period is 3 plus 2 plus 1, which is 7. Which is 6, sorry. Which is 6. So the average of y is 6 over 3, and that is 2. This is y, not x, sorry. Okay, so this is, so now we have energy, we have power, and we have average. Now, another one concept is called even and odd signal. We say that the signal x is an even signal if x n is equal to x minus n. So if we plot this, okay, the plot of an even signal may look like this. So if suppose you are given this, it has to be an mirror image of itself between left and right. Here, this is an even signal. Okay, this is an even signal. You see, the left and the right are images of each other. Now, if for an odd signal, then the left and right, not only do they have to be images of each other, you have to flip it down. Okay, you have to flip it down to be the mirror image of each other. So an odd signal may look like this. You see, this is an example of an odd signal. You have to flip it vertically for them to be mirror images of each other. All right. So this is an odd signal. Now we can do composition. Okay. Even an odd composition, any signal x can be written as an even component plus the odd component, where the even component can be computed using this equation. So you add xn with x of minus n, and then you divide it by 2. Whereas the odd component xo can be computed as xn minus x of minus n. Okay, there are two minuses here. The first minus is here, and the second minus is here. Just subtract them and then divide the subtraction by 2 to get the odd component. So any signal could be decomposed into these two components, and you add these two components, the even component and the odd component, you add them together, you're going to get a signal x of n back. For example, here in this signal, you see, if you compute the xe using this equation, you'd get this one. But if you compute the xo using this equation, you're going to get this one. And if you add these two together, you add them, you're going to find that you're going to get the same signal back. So we say that this is decomposed into this one and this one. Okay, one is even and the other one is an odd component. Okay, I don't know why this one shifts up. Now the time transformation, the transformation, the first transformation is time reversal. We say that y is a time reversal of x if yn is equal to x of minus n. Basically, what you do when you're doing a time reversal is that you flip it horizontally from the left to the right and right to the left. For example, here in this signal, if you do the time reversal to get x of minus n, this sample is switched to here, whereas this sample is switched to there. So you swap these two together, you swap these two together, and you swap these two together, and you're gonna get this one. Okay, you see, they are time reversal of each other. All right. Let's do another example. Now let is that right? Xn equal to 0.3 to the n, where n is 0, 1, 2, and so on, and 0 elsewhere. Then time reversal would be x of minus n, right? So you just replace every n you see with minus n. So you're going to get 0.3 to the minus n, where minus n is 0, 1, 2, and so on, and 0 elsewhere. So 0.3 to the minus n is 1 over 0.3, and that is about 3.33 to the n, where n is equal to 0, minus 1, minus 2, minus 3, and so on. Okay, I think I should do this. 1 over 0.3 to the n. Okay, so yeah. So graphically, it be this. Now, if we do the time reversal, time reversal becomes this, so on here. So the top one is x of n, the lower one is x of minus 1. I think I should write down 0, 0, 0 here, and 0, 0, 0 here, and so on. Here. Okay. Another one is called time scaling. Okay. Yn is a time scale of xn if yn is equal to x of minus a, x of an. No minus sign. X of an. X of an. X of an. Okay, so we can scale it in. There are two ways to scale it. Either you expand x or you shrink it. You condense it or you expand it. Now, there is a condition because of the condition that everything inside the bracket has to be an integer. So you have to be careful when you shrink it, because when you shrink it, you basically are multiplying the value of n by some fractions, right? Now, if the multiplication becomes a fractional number, then that would not be valued, and that sample would have to be destroyed or disposed. For example, here, you see, starting with this signal, right? You are doing x of 2n. So when you do x of 2n, basically what you do is you are condensing it. Now this sample is just the same, whereas this one will be moved from 2 to 1. So this one here, I'm gonna shade it for you. This sample is this one. Okay. Now the brown sample stays the same because n is 0 for the brown sample. And the green sample 2 here becomes this one. Now the pink sample here though is gone. There's nowhere for it to be, because if you multiply 1 by 0.5, it should have been here. It should have been here, but because of the restriction that n has to be an integer and this one is 0.5, so you cannot write it down there. Okay, so this sample will be disposed of. Same for this one and same for this one. Yeah, so when you do condensing discrete time signals, you have to be careful, okay, of the loss of information here. I'm saying it as a loss of information because these pink samples are lost. Okay, when you do condensation. But if A, now this one, for this one, A is greater than 1, but if A is less than 1, means that we are expanding it. So going from this one to this one, we have x of n over 3. Basically, what you do is, for x of n over 3, you multiply each instance by 3. So 1 multiplied by 3 is 3. 2 multiplied by 3 is 6. Minus 1 multiplied by 3 is minus 3. And minus 2 multiplied by 3 is minus 6 here. Okay? So there are no loss of information here in this case. But these instances are not defined now. Okay? Because there are no instances, there are no samples here for this. There are no samples here for in X to begin with, so you don't have samples in these instances. Okay, there. You see, the brown one. Oh, sorry, the brown one is here. Okay, I think I should erase this and this one to make them distinct. Which one haven't I used? Yellow. So a pink one and the blue one, okay, and the green one, the brick gray one and the green one here. All right. So this is called time scaling. The next one is called time shifting. Time shifting is easy. You just shift it left or right by adding n by some constant. If n0 is positive, then you are shifting it to the right. But if n0 is negative, then you're shifting it to the left. So for example, if you say that y1 is equal to x of n minus 2, then this is just shift. Y1 is just x, n shifted to the right by 2 samples. Shifted to the right by 2 samples. Okay. On the other hand, if we have y2 equal to x of n minus n plus 2, then this is shifted to the left by 2 samples. Okay. Here, if we start with this one and we have x of n minus 2, then this sample, the brown sample goes 2 samples to the right. The blue sample goes 2 samples to the right. The green sample goes 2 samples to the right. The pink sample goes 2 samples to the right. What else? The yellow sample here goes here. And what do we have? What else do we have? I've run out of color. I think I should have this one here. Okay, right. 2 samples to the right. Okay, shift it. On the other hand, if we do this, okay, then we're shifting it 1 sample to the left. So the brown one is here, okay, and the blue one is here, and the purple one is here, and the green one is here, the pink one is here, and the yellow one is here. Now this is shifted 1 to the left. This is shifted to the right 2 samples. Okay. Now let's do an example. Now here we are doing time transformation. Uh, let's say that we start with the signal x and we are trying to do x of 2 minus n. Okay, so this is xn. Now let's erase this one to make it xn. X of n. Now to draw this graph, what you do is x of 2 minus n is equal to x of minus n minus 2. So the first step is to do this. Do the time reversal first. And then what you get is you shift it to the right by 2 units. Okay. Here, you see, from here, right? Now you do the time reversal, you're gonna get this and this and this. Now if you do time reversal, now you shift it to the right 2 units, then this one is here, this one is here, this one is here, and this one is here. Right? Yeah. Okay, we have this one, we have this one, we have this one, and we have this one. Now we do the time reversal, right? So from the time reversal, we shift it. Okay, so this one goes here, this one goes here, this one goes here, this one goes here. Not, yeah, okay, and this one goes here. Okay. So in general, what you do, in general, okay, to plot x of a n minus b. Okay, first plot x of a n. But first is to write x of a n minus b over a. If a is minus 1, then it is just the time reversal. Then plot x of a n. Okay. Shift result from step 2 to the right by b over a samples. Now be careful, if b over a is negative, then instead of shifting right, you shift left. By absolute b over a samples. Okay, now in this example, a is minus 1. In this example here, a is minus 1, right? And b is minus 2. So we have that. Okay, right. Now, for example, okay, suppose we have y of n is equal to x of minus n minus 4. then the first step, write x of minus n plus 4. The second step is to plot x of minus n. The third step is to shift whatever you have to the left by 4 samples. Okay, then you're gonna get the plot of y. All right. Another transformation, another operation is called amplitude transformation. In amplitude transformation, we can scale it and we can shift it down, up or down. A is the scaling factor and B is the offset. Okay, the constant A determines the amplitude scaling and the constant B determines the amplitude shifting or the offset. All right, for example, here, okay, if we start with xn like this, then we want to find y, which is equal to 3 minus 2xn. So the first step to do is to multiply each sample of x by minus 2, and next we're gonna shift it up by 3. So first multiply every sample by minus 2, and then add result with 3. Okay, to get this one. And you have to be careful when x is 0. This one is not 0 anymore because you have to add it by 3, right? So 0 plus 3 is 3. 0 plus 3 is 3. But you have to be careful not to write down 0. Okay, all right. So for example here, 1 multiplied by minus 2 is minus 2, right? And then minus 2 added by 3 is 1. 2 multiplied by minus 2 multiplied by minus 2 is minus 4. Minus 4 added by 3 is minus 1 here. 0 multiplied by minus 2 is 0. 0 added by 3 is 3. Right? So this is what we do from the definition here. All right? And we can also do both. Okay, we can do both the time and amplitude transformation simultaneously. For example, if we start with x, then we can, and we want to find y, which is equal to 3 minus 2x of 2 minus n. So first you might want to do this one, right? And once you got this one, then you do the amplitude transformation. So first do the time transformation. To get x of 2 minus n, and then do the amplitude transformation on what you have, x of 2 minus n. So if we start with this x of n here, okay, we start with this one. Now let me draw it here. Then we do the time transformation to get this one. So remember how to do this one. what we do is we write x of minus n minus 2, right? Oh, x of 2 minus n is equal to x of minus n minus 2. So what we do is we do the time reversal and you shift it to the right by 2 time units. So what we have here is x of minus n, like this. X of minus n would be this, 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 and this. This is x of minus n. Then you shift it to the right by 2, right? So what you have is, oh, shift it to the right by 2. So what you have is, oh, sorry, here, shifted by 2. This is 0, 1, 2, 3. Okay. Yeah. So this is x of 2 minus n. Then what you do is we do the amplitude transformation now. Multiply by minus 2 and then shift up by 3. So y would be here. Multiply by minus 2 and shift by 3 is 3. So we have 3. We also have 3 here. And this one is 2, right? This one's 2. So 2 multiplied by minus 2 and shift up by 3 would be minus 1. Okay, would be minus 1. Okay, this one is another 3. This one is 1 multiplied by minus 2 is minus 2 and shifted by 3 would be 1. Okay, and for 2 we have 3. 2 multiplied by minus 2 2 multiplied no, here 1 2 multiplied by minus 2 is minus 4. Minus 4 plus 3 is minus 1. This is 1. 1 multiplied by minus 2 is minus 2 and shifted by 3 is 1. So we have this one. This one is too small. They have to be the same size. Is that right? Yeah. Oh, sorry. The first one is correct here. So we have 1 minus 1. No. What do we have? This one is 3, 3, 3, and 3. Again, let's do it again. 0 multiplied by minus 2 is 0, plus 3 is 3. 0 multiplied by minus 2 is 0, plus 3 is 3. 2 multiplied by minus 2 is minus 4. Minus 4 plus 3 is minus 1. And 0 is 3 again. Now 1 multiplied by minus 2 is minus 2, plus 3 is 1. Okay, and 2 multiplied by minus 2 is minus 4, plus 3 would be minus 1. So this one is not correct, has to be minus 1. And then 0, 0 are the rest. So this is why n is 3 minus 2 x of 2 minus n. We're performing the amplitude transformation on this one. Taken here. Okay. Now let's talk about some standard discrete time signals. The first one would be the unit sample function. The unit sample function is analogous to the unit impulse signal in continuous time signals. So the unit sample signal or discrete time unit impulse is defined as 1 when n is 0 and 0 when n is not equal to 0. And the symbol for the unit sample signal is the delta symbol. So delta of bracket n is 1 only when n is 0, the rest is 0. So if we plot the graph of the unit sample signal, we see that there is only one sample here, which is 1, the rest is 0. Of course, we can do the time shift. All right, we can shift it to the right or to the left. Now in this example, we are shifting it to the right by n0. Now let's look at an example. In this example, we are drawing a graph of this one. So let's draw a graph. No, before doing it, let's look at this graph. Okay, this is equal to delta n plus delta n minus 1 plus delta n minus 2 plus delta n minus 3 and so on. See, this one is k equal to 0. This one is k equal to 1. This one is k equal to 2. This one is k equal to 3 and so on, because k goes to infinity. So basically we are adding these signals up. Now the first one is just the same. This is just delta n. That's the first one. The first one is delta n. The second one is delta n shifted to the right by one sample. So this is the second one. Okay. The third one. The fourth one. And so on. Whereas for n negative, we have all zeros. So this is this is the graph of xn. And another example, this one. Now for this one, we have this one is equal to dot plus delta minus 3 plus delta minus 2 plus delta minus 1 plus delta 0 plus delta 1 plus blah 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 plus delta n. Okay, but you see this one is 0. Okay, this one 0 0 0. This one is 1. This one is 0. This one is 0. So overall here, if you add them up, okay, the result will be 1 if n is greater than or equal to 0, and it is 0 when n is 0. So this one, the value of this is 1 whenever n is greater than or equal to 0, and it is 0 else because here you see, if n is negative, then the summation would never go beyond negative times, because when n is negative, right, it ends at n. But if n is positive, then you can have this sample in your summation and the result would be 1. Only this one is 1, right? So you got to have this sample to make it 1. And the only way to make this sample, the only way to have this sample in your summation is when n is greater than or equal to 0. So that's why we have 1 when n is greater than or equal to 0, and 0 when it is not. Okay, so the graph of this one and this one are basically the same. So this one is this graph, right? Basically, so they share the same graph. Their graphs are identical. Another signal is called the discrete time unit step. The discrete time unit step has a value of 1 whenever n is greater than or equal to 0, and we use a symbol u to stand for the unit step signal. You see, this one is just here. So you could write, it turns out that you could define a unit step discrete time signal using this summation or this summation, okay, here. That's why I wrote it down here. Okay, of course, you can shift a unit step signal. This one is shifted to the right by n0. So starting with here, shift it right by n0, you get that one. So you can shift it right or shift it left. Okay. Also, see, un and un minus 1, and now let's subtract them. Okay, suppose we plot, I'm now plotting un. So un is this is un. This is un. And un minus 1. This is un minus 1. Now, if we start with this subtracted by this one, what are we going to get? We're going to get only this one, right? This, because this one's 1 minus 0 is 1. The rest is 0. So we subtract them. If we subtract them, we're going to get only this one. We're going to get only this one, and the rest would be 0, because the rest is just 1 minus 1 or 0 minus 0, and it is 0. This is un minus un minus 1. And you see, this is just delta n. Okay. In general, delta k is u of no, not general, just this one. All right. Now, this is discrete time signals. Now we're going to talk about discrete time systems. The discrete time system is just a system whose input and output signals are discrete time signals. So if we draw a diagram, okay, this is a discrete time system. This is the output, this is the input. Now, for it to be a discrete time system, both the input and the output have to be discrete time signals. So the input is a discrete time signal, and we denote it by x of n, and the output is also a discrete time signal, or dt, and we denote it by y of n as the output. This is the output, this is the input. This is a discrete time system. For example, we usually name it T for discrete time system. So this notation stands for Yn. This notation means that Yn is the output from the system T when the input is Xn. So we're applying the signal, the discrete time signal Xn as the input to the system T, and the system T will respond with the output signal Yn. And in this case, okay, this system, what it does to the input signal is it squares the input signal, okay, and the result from the squaring is going to be the output signal at the same time n. All right, so what it does here is simply squaring the input signal and make it the output signal. So for example, if the input signal is a if the input signal is a to the nun, okay, whenever I multiply some function with u, it means that I'm starting it at time 0, okay, just as in continuous time system signals and systems. Here I'm multiplying by u, I'm multiplying a to the n by u, so basically I'm starting a to the n at time 0. So if I apply this signal to this system, then Yn would be a to the nun square, and that would be a to the 2n un. Okay. Now I'm gonna leave this one as a homework for you to read, so I'm gonna skip it. Okay, please read it. Now, properties of discrete time systems. The first property is called linearity, just as in continuous time systems. For a system, let T be a discrete time system, and Y1 is the response from X1, and Y2 is the response from X2. Then the system T is linear if the output from the combination is the same combination of the output. Okay, so output. So if we write down the diagram, if we apply A1 X1 plus A2 X2, then the result would be the same as we do the same combination on Y1 and Y2. if we have the linear system here. Okay, now these systems are linear. Okay, these are linear systems, examples of linear systems, and these are not linear systems. You see this one, I would like to point it out, this one. Now, a necessary condition for the system T to be linear is that if we apply 0 as the input, the output has to be 0. Okay, here in this case, you see, whatever the input is, the output is 1, right? So even though the input is 0, the output is still 1, so this one is not linear. Definitely not linear. This one as well. If you apply x equal to 0, you see y equal to 1, but that violates this condition, so this one is not linear. For it to be linear, this one has to be true. Whenever the input is 0, the output has to be 0. This is a necessary condition. But here, you see that this one, if x is 0, y is 0. But how come this one is not linear? Because this condition is necessary, but not sufficient. It is only necessary. It is still not sufficient. If you can say that this is not linear, but you cannot say that this is linear. Looking at this equation, look at this condition. You have to further test it for it to not be linear. Okay. Right. Time invariance. The concept of time invariance in discrete time systems is just the same as the concept of time invariance in continuous time systems. Basically, a time invariant system is a system that has the behavior of such system doesn't change with time. Okay, the behavior of the system is invariant to time. How the system responds to a particular input doesn't change with time. Okay, for example, if you give the input at time 0 and the output is a certain signal, then if you give the input 1,000 samples further ahead in the future, the output would still be the same. Okay, the output would still be the same, except that it would shift to the right, inconsistent with the time at which you apply the input, but the shape of the output would not change. Okay, because the shape of the output indicates the behavior of the system, right? And that is basically time invariant system. To test whether a system is time invariant, you do this. First, you apply the input x to the system, right? And you got the output y, and then you delay the output y to get this one. Now keep that in mind. The second branch is you apply the same input, but now you switch these two around. Okay, so instead of putting system here, you delay it first. You delay the input first to get this one, and now you apply this one to the system to get this signal. Now, if these two are the same, then your system is time invariant. But if these two are not the same, then your system is not time invariant. Just as we did in the continuous time version. Now, these are examples of time invariant systems, and these are examples of time invariant systems. You see, one trick that can be used is that whenever you are messing with inside the bracket, whether you do scaling or you time reversal, then your system will not be time invariant. But time shifting is okay. So I can say that time scaling or time reversal will result in system being not time invariant. But time shift is okay. Okay. Also, multiplying by n would give you time variant system. Okay. All right. Stability. Discrete time system is stable if whenever you have a bounded input, the output is also bounded. Now, what do I mean by bounded input? By a bounded signal. A signal is bounded if there exists an integer n, capital N, such that the magnitude of x doesn't exceed n for all samples. Every sample doesn't. The magnitude of every sample doesn't exist. Doesn't exceed n. If there exists such n, then your discrete time signal is called a bounded signal. Now, T would be a bounded input, bounded output, or bistable if whenever X is bounded, the output is also bounded. Okay, now these are examples of bistable systems, and these are not bistable systems. All right. Okay. Causality. Discrete time system is called causal if the output at the present time depends only on the input. Well, the output at present time does not depend on the input at future times. So output at present time does not depend on inputs at future times. This is the essence of causality. If the system is causal, then this is what it means. So these are examples of systems that are causal. See, look at this case. The output at present depends on the input at present, right? The output at present, which is n, depends on the input at present, which is n. But here, this one's not, because if n is negative, then minus n is positive. So yn, y minus 1 equal to x1. You see, because 1 is future, right? Minus 1 is past. So the output at present, let's suppose that present is minus 1. The output at present depends on the input in the future. So this one is not causal. Okay, not causal. This one as well. This one is not causal because the output at n, which is the present, depends on the input at n minus 1 and n plus 1, which is future. So this is present. This is future. The value of the present here in this case depends on the value in the future, so it is not bistable. All right. Memoryless. Memoryless is easy. The output at present has to depend only on the input at present, not future, not past. So memory system, every memoryless system has to be causal, right? Has to be causal, because causal, the condition for causal is that it doesn't depend on in the future, right? It doesn't depend on the input in the future. But memory system is stricter, is more strict than that. It doesn't depend on the past and on the future. So memory systems have to be causal. Now these are not these are not memory systems, but these are memory systems. Okay, sometimes a system that is not memoryless is called a dynamic system. So whenever you see a dynamic system, it means that it is not memoryless. Okay. Now the last example. Now let's look at the system defined by this equation. Okay, is it linear? Yes, it is linear because it depends on x, right? This is just a constant. This is just a constant. If you do a linear combination, then y is also the same linear combination. So yes, it is linear. Okay, is it time invariant? Is it time invariant? No, that's because the scaling that you multiply to x depends on n. So if you, let's say if n is equal to 0, then it would be the scaling factor would be 2.5 over 1.5 squared, right? But if n is 1, the scaling factor would be 3.5 over 2.5 squared. So the scaling factor depends on n. Hence, the behavior of the system depends on n as well. So it is not time invariant because the behavior depends on n. Is it stable? So it is it stable? Is it stable? Is it stable? Yeah. Is it stable? Is it causal? It is causal. Is it memoryless? Yes, it is memoryless. But is it stable? Now, let's look at this. Is it stable? Now, when n goes to infinity, this one goes to xn. So it is stable. Okay, it is stable. Because when n goes to infinity, y goes to xn. That's because the reason is because absolute yn is equal to absolute n plus 2.5 over n plus 1.5 squared times absolute xn. And you see this is bounded by bounded by what? The factor here, if you plot the factor here, it will decrease with n. So pick a number is not greater than 10xn. So whenever xn is bounded, yn is also bounded. Okay? Because here, if n goes to infinity, right? This one goes to 1. Okay? But if n is 0, this one is 2.5 or 1.5. So there has to be a maximum value for this one. Let's say it is 10. So yn is bounded. So the system is stable. All right. So this concludes discrete time signals and systems. In the next lecture, which is on Tuesday, we are going to talk about linear time invariant discrete time signals and systems. I'm sorry, linear time invariant discrete time systems. So please don't be late. All right, here, do you have any question before we finish? Okay, so if no questions, we'll meet again on Tuesday. Until then, bye bye. Have a great weekend.
สวัสดีครับอาจารย์
ครับสวัสดีครับ